Hi, welcome to the third lecture video for transition elements, and we are going to start off from the polydentate ligands here. So we're going to see some examples for the bidentate as well as the hexadentate ligands. All right, let's go. A bidentate ligand is one which can form two dative bonds or coordinate bonds with the central atom or ion. We will need to know some of them, so get ready to memorize a little bit. The more or most popular one I would say is ethane 1,2-diamine. Okay, we usually call it EN in short. Okay, this is the one where we have an ethane molecule with two hydrogens being replaced with a amine group, functional group. Okay, and take note where the two lone pairs are. Okay, so this molecule actually can bend around, by the way, because these are tetrahedral shapes and this is a trigonal pyramidal shape with respect to the nitrogen. So it can bend and turn such that it can actually grab onto the metal ion or atom. Okay. Another one will be your ethane diovate ion, also called oxalate ion. So based on the shape of this ligand, you can see that due to the trigonal planar shape, it allows the two oxygen to actually kind of like grab onto, form dative bonds and kind of like grab inverted commas, okay, to a metal ion. Okay, and lastly is your 2-hydroxybenzoate ion. Okay, see how close the two oxygen with the lone pairs are. So the metal ion will be here. Now in this example, okay, it showcases how En can form the dative bonds around a cobalt 3+ ion. Okay, so because you are utilizing three bidentate ligands or three ENs here, so you need to know how the ligands actually binds to the cobalt 3+. So take note that okay, let me move my laser pointer to here. So take note that they usually bind in a 90-degree fashion. All right, and you got to remember that the molecule technically can bend around, okay, but it cannot stretch. So it cannot go and do a 180 degrees bind to the two axial positions. Cannot. Okay, so usually it's about 90 degrees because bond lengths and angles has to be kept optimal. Okay, so you can think about it as taking a 90 degrees here. Okay, and then this one will take a 90 degrees to the bottom axial position. Okay, and then that leaves the two remaining equatorial positions here for the third EN. Okay, and similarly for your ethane diovate ion, which is called oxalate here, okay, it's a similar fashion here. Okay, so it cannot, the ligand cannot bend all the way 180 from two axial position. It's not possible. Right? So it's like 90 degrees to each other, right? So they'll take this position, and you basically is you need to know what is the coordination number, okay, of this complex ion, which is 6, and there are 3 bidentate ligand, okay, and you need to know how to draw them, okay. So you need to know how to draw this structure if the question asks for it. Now we move on to a hexadentate ligand, and this is a crowd favorite. We call this EDTA. Okay, hexadentate ligand basically is one that can form 6 dative bonds per one ligand. One molecule can form 6 dative bonds, okay, with a central atom or ion, right? So this famous hexadentate ligand is called EDTA, ethylene diamine tetraacetate. Okay, and those of you who know the formal name for acetate is ethanoate, by the way. Yeah, okay, this is the ethanoate part, CH 2COO minus. Okay, why is it not CH3? It's because one of the H is replaced with this part. Okay, the original it's like En. Okay, but the NH2, right, instead of a H2, they have been replaced with a ethanoate part. Yeah. Okay, so this is a very interesting ligand. Okay, so let's see what it can do. Right, and this is how an EDTA ligand wraps around the central metal atom or ion. So we have a copper 2+ here, okay, and you can see how it wraps it such that the 4 oxygen, these are O minus, O minus, O minus, and O minus, and your neutral nitrogen here, and with lone pairs on them, okay, they are able to wrap it around in a octahedral arrangement. So this is a very fantastic thing. EDTA is actually one of the most powerful chelating agents and used in medicine therapy, whereby it can help to remove toxin due to this feature. Okay, all right, and then the thing to note is that EDTA has a 4 minus charge because of this 4 oxygen. 1, 2, 3, and 4. So altogether it's 4 minus. So hence, if you check this overall charge, right? Okay, with copper 2 plus, it will be 2 minus. So do take note of this. Right. This is an example where EDTA has been used. So it comes in the form of a disodium EDTA. This is I I'm not sure what this is actually. Okay, but it's definitely food. Okay, yep. Okay, let's go through that. Okay, so EDTA 4 minus is a useful ligand. It's used in many situations to mop up metal ions, such as salad dressing. Yeah, okay, salad dressing to prevent food spoilage. Okay, it's also used as an antidote. Okay, like what I mentioned just now. Okay, for heavy metal ions and to help prevent blood from clotting during operations by chelating with calcium ions. So EDTA is a very, very useful ligand here, okay, in society. And interestingly, it's also used in Pantene hair fall conditioner. Hair fall control conditioner. Yeah, disodium EDTA is actually found in the ingredient list. Okay, this is added to shampoo to help soften the water. And when we say soften the water, means remove the ions such as Ca2 plus and Mg2 plus from hard water. So there's this chemistry concept about hardness of water. You can actually do a Google search on what is that idea about. It's quite an interesting thing. Okay, and with that, we have arrived at the end of the list of ligands to note. So next we'll talk about the stereochemistry of complexes, which means the shapes of the complexes form. Okay, so for the shapes of the complexes, it depends on the coordination number. Okay, and okay, so let's go through the list. Okay, it's actually quite a simple concept here. So if you know the shapes from chem bonding well, then this shouldn't be a problem. Okay, so for coordination number 2, okay, it will adopt a linear shape for the complex ion or complex. Okay, so for example, okay, Tollens reagent, which is your diamine silver 1, right? This will be how you draw your complex ion for this. Similarly, for CuCl2 minus, okay, this will be how you draw it. Okay, so you have your dative bonds pointing from the atom with the lone pair, okay, to Ag, right, and from Cl to Cu, right. So your ammonia needs to invert, okay, the formula so that the atom with the lone pair will can have the dative bond drawn from it. Okay, next up will be the tetrahedral shapes, which belongs to coordination number 4, right? So we have examples like CuCl4 2 minus and CuCN4 3 minus. Now we have another type of shape for the coordination number 4, and that will be a square planar. Okay, and we have a very classic one called transplatin. Okay, this transplatin. Okay, so to understand which shape the 4 coordinated complex will be, okay, either tetrahedral or square planar, right? Okay, actually there's no formula, no way out. Okay, so if you look at the lecture notes and watch out for the formula that is associated with square planar and those that are tetrahedral, okay, you just have to memorize it by heart. Really just memorize it by heart, right? And those examples are the ones that generally will be used in your exams. Okay, so don't have to worry too much about the special one. If there are special ones, I'm pretty sure the examiner will give you hints about it. Now we have the most common one, which is the octahedral 6 coordinated complexes or complex ions. All right, and we have examples like this. Okay, this is hexacyanoferrite 2, and this mega one, okay, with the 3 bidentate ENs. Sorry, not EN, sorry. These are your ethane diode ions. Okay, So these are your examples of 6. Okay. Okay, last but not least, we have this ion that you found uh, after adding what's that? Aqueous ammonia in excess to copper 2 plus. Okay, if you add it in dropwise, for this you'll get a blue PBT that dissolve in excess ammonia, okay, to form a dark blue complex solution. I mean the solution is contains this complex which is the dark blue, which is in dark blue color. Okay, so interestingly, you will actually see how the water is actually having a very long arrow here. Okay, there's a reason for it, but you don't need to know that. Okay, it's not in your syllabus at all. Okay, now for you, it is actually also not required for you to memorize where to position the ammonia and the water. Okay, so long that you know there are 4 ammonia and 2 water in the octahedral fashion, that will be good enough. Okay, so you don't have to worry too much about how to position the ligands. Now we have arrived at one of the most important parts of this chapter, which is about colors of the transition metal complexes. All right, and you are going to learn a very new theory or new concept here. So get ready, okay, buckle up, and let's see what we have in this video.
Giurgevak zelení, Giurgevak zelení, svýma osimení zelení. Come sarà moja draga, na Giurgevak miriše, na Giurgevak miriše, meni nikad više miriše. Proslavit ću Đurđev dan, proslavit ću Đurđev dan, proslavit ću Đurđev dan, on my own. Proslavit ću Đurđev dan, proslavit ću Đurđev dan, proslavit ću Đurđev dan, on my own.
Đurđev dan je svima osim meni, Đurđev dan je zeleni, Đurđev dan je svima osim meni, zeleni.
Nice. All right. So you can see how different types of ligand can actually form so many different colors for nickel 2 plus ion, right? Nice. Very nice. Now for this segment, you will have to learn a little bit of physics, yeah. Physics in terms of learning the electromagnetic spectrum. Okay, so let's give ourselves a chance to learn how this concept, okay, from the electromagnetic spectrum can be used or applied to chemistry. Okay, so let's learn about how colors originates. Okay, so color is actually within the visible spectrum, okay, which is here, within the electromagnetic spectrum. Okay, so in the electromagnetic spectrum, okay, you can either see by wavelength or see by frequency. All right, okay, and for wavelength, okay, okay, this is the part where we have the longest wavelength. So you can see it's from 10 to the power 1 to 10 to the power minus 1, and then move on to 10 to the power minus 15. Okay, and that is corresponding to the highest frequency here, 3 times 10 to the power 22. Okay, so how many, like total, how many crest, and so I think, yeah, how many waveforms are there in per second. Okay, so frequency can be seen as hertz as well, Hz, yeah, hertz. Okay, so here for wavelength, okay, the waves, okay, or the electromagnetic wave that has the longest wavelength is radio waves. Okay, and as we go to the right, okay, we will have a decreasing wavelength. Okay, so try to follow one or the other. Okay, it goes opposite. Okay, so after that will be TV waves or TV, which is actually a form of radio wave, to be honest. Okay, and then after that is microwaves. Next will be infrared radiation, okay, where some of us learn it as heat, okay, for a certain zone within this electromagnetic spectrum. Okay, visible light will be here. Okay, next one will be ultraviolet, X-ray, gamma ray, cosmic rays. Okay, all right, and for no, sorry, not ultraviolet, for the visible spectrum, okay, you got to learn which color correspond to a longer wavelength and which one correspond to a shorter wavelength. Okay, so for red, okay, red is the longest one, so okay, we need to learn it in sequence first. Okay, so red, orange, yellow, green, blue, indigo, violet. Okay, and it's good to actually know the range of wavelength for visible light. Okay, it's also seen as white light. So it's from 430 nanometer to 670 nanometer. Okay, 430 nanometer is the wavelength, the shortest one, so it's over here, and 670 nanometer is over here for red. Right. So for us chemists, okay, we will learn the sequence of the colors. Now for colors, right? Okay, we need to understand that is the way our eyes receive the wavelength, okay, and then our brain interprets the color from there, okay. And we also it's also good to know how a white opaque works to us and how a black opaque object will work. Okay, so for example, if you have white light, okay, shining onto a white both objects, in this case, okay, for a white opaque object, you have all the wavelengths reflected, okay, from the surface, okay, to our eyes. Okay, so when you see that you have all the wavelengths gathering or concentration towards our eyes and our eyes receive it, okay, it will be seen as white. For a black opaque object, none of the wavelengths of light has been reflected from it, so we can't see it. So we call this object absorbing light, okay, or absorbing the white light, so it looks black. Okay, like this. Next, for transparent object that is colorless. So for an object that is transparent, it means that light travels through it, okay, or transmitted through it. So if all the wavelengths of visible light is able to transmit through it to our eyes, then that object will appear colorless to us. Okay, how about an orange opaque object? So which means to us it will appear orange. Okay, so which means we are not receiving all the wavelength of light from white light that was incident onto the object. So what happens here? Okay, so if you were to see an orange object, what happens essentially is that the blue component of visible light has been absorbed. Okay, the blue component has been absorbed and the other wavelengths has been or have been reflected to us. So the combination of those reflected wavelengths will be orange to our eyes. Okay, and orange is the complement color of blue light. And how do we know it? Because there is a certain color wheel we can use, okay, to help us see it. Okay, so a quick simple way to see that orange is the complement color of blue is that in this circle, you got to break it out into 6 parts. Okay, red, orange, yellow, green, blue. Indigo is part of blue, so you just leave it as blue, and violet. So technically 6 different zones. You can go clockwise or anti-clockwise, doesn't matter. You arrange this according to that rainbow sequence that we learned. Okay, and then you'll notice that orange and blue are opposite to each other. So orange is a complement to blue. So if blue is being absorbed, okay, for the wavelength or the component is being absorbed, then it will appear orange. Likewise, if green is absorbed, you'll see red. If you absorb red, you'll see green. So technically, this is a guideline on how this works. This is a very simplistic color wheel, so do take it as a simple guide. It is not I mean, there are so many different types of color wheels out there, so this is the baseline we'll use. Right, we have another infographic showing how transition metal ions can have different colors. So for titanium 3 plus, we can see as purple. Vanadium has 4 different colors. 2 plus is purple, 3 plus is green, 4 plus is blue, 5 plus is yellow, and so on. Okay, and chromium plus 6, yeah, is orange in the form of dichromate. Iron 2 plus is pale green, 3 is yellow. So this is the one that we some I mean some of the colors we have seen it quite often in our practicals already. Okay, but I want to bring your attention to the words here. Okay, in particular, I'm going to zoom into a paragraph. Okay, it says that okay for colors to appear, right, to appear for a transition metal ion, okay, you need to have ligands, and when you have ligands, some of the d orbitals become higher in energy than before, and some becomes lower. Electrons can then move between these higher and lower d orbitals by absorbing a photon of light, and this absorption of light affects the perceived colors, okay, of the compound or complex, and the wavelength. Or okay, so wow, this whole chunk, right, is what you are going to learn next. You are going to learn how this creates the colors that you see. Okay, all right, so get ready, people. Okay, so for this particular segment, here are the learning outcomes. So you're going to learn how to describe using the shapes and orientation of the 5d orbitals that I mentioned in lecture 1. Okay, and how that will bring about the splitting of degenerate d orbitals into 2 energy levels in octahedral complexes. So your syllabus only focus on octahedral complexes, and also to explain in terms of d orbital splitting and dd transition, why transition element complexes are usually colored. Big one here. This is a very, very big concept here. Okay, let's go into details why transition metal complexes are colored. Okay, sorry about my pointer. Okay, so let's look at an isolated gaseous metal ion with its 5 3d orbitals degenerate. So at this juncture, okay, you have a metal ion. We don't need to identify it, okay, but we know that it has 3D subshell, okay, that is all degenerate at the same energy level. Then inner complex, okay, when a central metal ion is surrounded by ligands. So this is a central metal ion, by the way. Okay, when it's surrounded by ligands, okay, and ligands, as you know from the previous part, each ligand has at least one lone pair to form a dative bond to here, right? Forming dative bonds to here. So you need to have empty orbitals here. Okay, so the 5 3D orbitals actually will experience electrostatic repulsion from the lone pair of the ligands. Okay, so what happens is, okay, when you have this thing called spherical ligand field, meaning when the ligands approach, okay, the metal ion, okay, that space here, okay, will have this electrostatic repulsion being as a part of the phenomenon. Right, okay, so let's move on. Okay, try to follow me from here. Okay, in an octahedral complex, okay, out of the 5 3D orbitals, 2 will actually experience more electronic repulsion than the others. So what happens is, this will cause the 5 3D orbitals to split into 2 separate energy levels, okay, and that will form an energy gap between them, which means it will be like this. Okay, 2 separate energy levels, one higher than the other. So you need to know is 2 above and 3 below. 2 orbitals being or being the ones to experience more electronic repulsion become so therefore becomes energetically more unstable than than the other 3. Okay, more electronic repulsion, less stable. Lesser electronic repulsion, more stable. Affects 2, affects 3. Okay, and the energy gap is seen as H mu. I think it's called mu. Okay, you can call it HV, but actually it's called HF. Planck constants times frequency over here. Okay, I'd like to draw attention to one electron within this system. Okay, so let's say this electron, right, in the isolated gaseous ion has always been residing in this 3D orbital, okay, and now it's at the lower group, okay. So when the ion is in the octahedral ligand field, technically it means that the ligands have surrounded this metal ion, okay, in the octahedral fashion already, okay, and they have formed with dative bonds, okay. So what happens is that when visible light of the right energy, okay, sorry, not visible light of the right energy, visible light is incident onto the metal ion. That means you will see white light. Okay, I can't draw white light. I'm going to use black. So when white light, okay, shines incident to the substance, which is this complex ion. Okay, what happens is you're going to just have the right energy to be absorbed. Okay, this particular wavelength, this particular energy gap here correspond to a particular wavelength in white light. Okay, because the white light has a range of wavelengths, right? And only one of it will be at the right energy to be absorbed. Okay, so when we say it's at the right energy, meaning, right, okay, you'll be absorbed by this electron, okay, and it will become excited. Okay, so let me erase this. Okay, I'm going to showcase how it works. Right, so to promote the electrons from a d orbital of low energy, so this is the electron that is absorbing that particular wavelength of light, okay, that corresponds to this energy gap. Okay, because for physics students, you learn that energy levels they are all in discrete levels. Okay, there's a fixed value to it, right? And that fixed value in this case, right, will correspond to that particular wavelength, okay, within white light, right? So what happens is you will get promoted to the partially filled or empty d orbitals of a higher energy here, right? You need to have a partially filled or empty d orbital here for the promotion of this electron that has gained the energy from that wavelength of light. Okay, and that is the energy gap that it will cross over. Okay, and as a result, the color observed will be the complement of the color absorbed. So if this color absorbed was blue, okay, then the other wavelength will be reflected off. That means they are not absorbed by this energy gap, right? I mean by this electron, because their wavelength is either lesser than this energy gap or more than this energy gap. So the electron will not absorb it. Okay, you will only absorb particularly for this energy gap. So hence, right, okay, if this energy gap corresponds to blue, what we will see is orange. Okay, so if you are confused, you may want to rewatch this part. Okay, time to learn some formula. Okay, the resulting energy gap between the two sets of d orbitals, it corresponds to particular frequencies of the electromagnetic radiation. So if it falls within the visible light, then the energy gap corresponds to a particular color, in short. Okay, and it's time to learn this formula. Okay, so I tend to see as HF, okay, but it's I think it's called mu. I may get it wrong, I'm pretty sure. Okay, so delta E is equals to H times frequency, as you can see here, of the radiation, or another way to see is HC over lambda, okay, where lambda is the wavelength of the radiation and C is the speed of light. Okay, and sometimes they may give lambda, so you need to know this formula as well. So physics students will know this well because when we learn about the electromagnetic spectrums stuff, right, frequency is inversely proportional to wavelength. So this is something that everybody should know by this point. Okay, often, okay, for transition metal complexes or compounds, the energy gap is often in the energy range of the visible region. So therefore, you will see colors due to this reason. Okay, yeah, so the color observed is a complement of the colors absorbed. Applying what we just learned last slide. So what this means is that if the energy gap is smaller, delta E is smaller, that corresponds to longer wavelength, okay, of lambda that has to be absorbed for this thing called d transition, which is the promotion of the electron from a lower energy d orbital to a higher energy d orbital. So in short, it's called d transition. Okay, so plug in this formula and apply to the color wheel. Okay, so ROYGBV. Okay, draw the color wheel and see which wavelength is complementary to the other. Okay, opposite colors will be complementary. So if you are seeing a substance that appears violet, like a titanium 3 plus solution, okay, that means that that solution is absorbing yellow light. Right, this is our layman way to call it. Okay, so you can use this one, right, to help yourself to understand how this works. Now we'll take a look at an example. Again, it's titanium 3 plus. Okay, equal solution. This is an ion with a D1 configuration lying at the center of a octahedral ligand field, and there is a machine that can be calibrated and used to detect the relative absorbance, okay, of the light that is shown through the solution. Yeah, there's a way to actually calculate how much light has been absorbed. Right, so we call this product. I mean, this is the what's that? The analysis that will be produced from the machine. So this is called the absorbance spectrum. Okay, and in this absorbance spectrum, it is plotted relative absorbance to against wavelength. Okay, absorbance to wavelength, and the wavelength goes from a smaller number to a larger number. So do take note that this corresponds to violet, and this corresponds to red. Red is about 630 nanometer. So you got to reverse the rainbow sequence in this case, to take note. Okay, now interesting is to just look at the peak will do. So it is actually showing a peak around the green yellow zone. Okay, as you can see somewhere here. So the complex absorbs most effectively in the green-yellow region, and it should appear violet because if you were to use the simplified color wheel here, okay, the yellow-green zone somewhat is around the violet-red part. Yeah, okay, you can guesstimate over here. So this solution should appear violet according to this, which is true. Yeah. Now we'll bring it back to the diagram that we have seen. Okay, so looking at the electron in titanium 3 plus, okay, now after ligands are present, okay, and forms the octahedral complex, then in terms of the splitting of the d orbitals, it will look like this. Okay, 2 above, 3 below with the electron, okay, here at the bottom because it's 3d1. So there's only one electron here, and there are 2 empty orbitals here, and there's an energy gap to cross. Okay, so the reason why this electron can be promoted to the orbital of higher energy is because this energy gap happens to be corresponding to the energy of green yellow light. Okay, the rest of the wavelengths will be reflected to, okay, and then if reflected to our eyes, then that will appear violet to us. Okay, now if we were to use another version of the absorbance spectrum, okay, for titanium 3 plus, okay, you can see that there are different graphs that can be plotted when the concentration is different. Okay, so for lower concentration, okay, your graph will be lower here, right, which is expected, right, because concentration is related to amount. So if your amount of titanium 3 plus is lower, then the amount of wavelength absorbance will be lesser as well. Okay, so I'm going to teach a little bit out of silver stuff. Okay, so first of all, the feature of the absorbance band, okay, is about its positioning. Okay, where is it positioned along the wavelength axis? Okay, that corresponds to the uh, color of light that has been absorbed. Okay, and the intensity. Okay, which is the peak, like this. So in short, we can relate absorbance to the concentration of the ion, and that brings us to this thing called the Beer-Lambert's law, okay, which is actually a formula to relate absorbance to the concentration of the ion in terms of C here. Okay, Now there are another two more variable. Sorry, one constant, one variable. Okay, epsilon is a constant which is called the adsorbance constant. So it's actually a value that is detected from various experiments done. Okay, and that is related to the substance that we are looking at. Okay, so you can actually refer this to a list of values. Okay, like a data booklet. Okay, and the length of the solution that the light passes through, which correspond to the crucible. It's actually a quartz crucible that you put the solution in before you place it into the instrument for it to pass light through. Okay, I don't have a picture right now. Okay, but generally that crucible, right, the path length is 1 cm. Okay, there is a fixed value, so that it's easier for us to simplify this calculation here. Alright, okay, I just got a random picture about this spectroscopic method called UVV spectroscopy, okay, which is the part that the Beer-Lambert's law was applied on. Okay, as you can see, there's a light source, there's a wavelength detector. Light source basically is your white light, and the sample is the one that I mentioned. Okay, this is the crucible, and the path length is 1 cm. Okay, for easier calculations. And then at the end there will be a computer, okay, that can process the detection and yeah, and then analyze and then produce the adsorbance spectrum. Okay, so if you want to check out more of how it works, just search for this word, okay, and then you can read it out on your own. All right, for transition metal complexes to show color, okay, due to DD transition, okay, your central metal ion must have the following. First of all, it must have at least one d electrons to be promoted at the lower energy level group of orbitals. Okay, must have at least one electron at the lower group, and a empty or partially filled 3D orbital at the upper level. Okay, so that's you can accommodate the 3D the electron that's promoted, because when the electron got promoted, it means that it has absorbed the energy from the white light radiation, okay, and then get excited, okay, to go towards the upper energy level, right? So you need that space at the upper group. So this actually shows something that you need to know, is that there are actually metal complexes, sorry, TE complexes or compounds that may not satisfy this condition. So if they do not have any of these condition, okay, these complexes and compounds can appear as white in solid form and colorless in solution. Okay, so one of the example would be the D0 configuration, meaning you have no electrons at all in the D orbital, right? And that will be your scandium 3 plus and titanium 4 plus. Okay, and because there's no electron in the first place, so you can't even do any DD transition, and there will be an absence of color in their compounds. So for scandium oxide, okay, it appears white, and for titanium oxide, titanium 4 oxide, okay, it will also appear white as well. This is the pigment in white paint, okay, as mentioned earlier on, and it's also one of the ingredients in your sunscreen protection or sunscreen lotion. Okay, next up is the other extreme, your D10 configuration, which will be your zinc 2 plus and copper 1 plus. Okay, in this case, you have many electrons, but you don't even have any empty or partially filled upper level to accommodate the D electron to be promoted. So DD transition is not possible in this case also. Okay, no color. So zinc oxide appears white, and copper iodide. Okay, if it's impure, it looks cream, but if you purify it, copper iodide actually will look white to you. Now, how about complex ions in the main group elements? Like for example, aluminium 3 plus with 6 water. So it's also a complex ion here. Okay, so this is the configuration of aluminium 3 plus. It ends with a 2p6. So first, okay, DD transition are not possible at all. We are not looking at D block elements right now. Okay, this is aluminium 3 plus. So it's a P block element. Okay, group 13. Right. So in this case, aluminium's D orbital, sorry. Aluminium's D orbitals are vacant. So there's no electrons there, right? So looking at the electrons that is present at its field 2p orbital, okay, if you look closely, the next one will be 3s, which is empty, right? So technically you can promote an electron from p 2p to 3s. Okay, however, okay, this is the next quantum shell, right? One quantum shell difference, which means the energy gap between the filled 2p orbital and the lowest unfilled 3s orbital is very large. So what does it mean? When it's very large, that means if you want to transit your electrons from 2p to 3s, okay, it requires the absorption of a much higher energy uh, radiation, which means into the ultraviolet radiation already. Yeah, okay, and that is outside of the visible region. So hence, okay, in terms of looking under white light, it will not be colored. Okay, so it looks white to us. However, this is the reason why some things looks colorless or on the surface, right? Okay, but when you shine UV light to it, it will luminescence. Yeah. So something along this line. Okay. Now, we are going to learn a new theory called the crystal field theory, and this is the theory that will explain why the d orbitals, right, will split into two separate energy levels in the presence of ligands. Okay, so let's see what we have here. Now the five shapes, the 5d orbital shapes, right? Okay, as mentioned, you need to know this earlier on. Okay, in terms of a coordinate system, right, it will look like this. Okay, so I want to draw your attention to the three at the bottom first. Is dxy, dyz, dsz. Okay, you need to know them, and the two here. Okay, dz square and dx square minus y square, right? And you may want to pause this video for a while and take a look at this part. Okay, when you are in the octahedral arrangement like this, okay, you can see the negative signs here. These are the so-called the point charges. Okay, crystal field theory focus on point charges, and this is where your central metal ion is. Okay, and now you are supposed to see how these orbitals are oriented within this space. Okay, get ready for the full explanation next. Now, if you are looking at the octahedral complex, okay, the ligands are modeled as 6-point negative charge. Okay, these 6 points that surrounds the positively charged transition metal ion. Alright, so your z-axis pass through vertically like this. X will be here through two ligands, okay, with the metal ion in the middle, and then Y will be like that. Right, then they are all 90 degrees to each other. Now let's take a look at two particular d orbitals, which is your dz square, this one, and dx square minus y square, which is this one. Right, now for these two particular orbitals, right, their lobes are within the region of the negative charge. So if you look closely, the dz square lobes, right, is having a head-on orientation towards the negative point charges. And take note, orbitals are supposed to be negative charge because of the presence of electrons inside. So this actually signifies head-on repulsion. Okay, then for the x square minus y square, same thing. Okay, the lobes are within the direction or orientation of the negative charges or negative point charges. Yeah. Okay, and as a result, okay, these orbitals will experience greater repulsion between the orbitals on the ligands. Okay, and these two orbitals, and as such, right, these two orbitals will get destabilized and move towards a higher energy level, right? So hence 2 above. Now on the other hand, okay, the other three, okay, the dxy, this one, dxy, dyz, this one, and dxz, xz is this one, yeah. Okay, their lobes are actually projected in between the charges. Okay, you can see it's actually diagonal to the coordinates, the xyz coordinates. So kind of like they avoided it, right? Yeah, their orientation is different. So as such, the repulsion is still present. Again, there's still repulsion between the orbitals, okay, on the ligands as well as these three particular d orbitals are still got repulsion, just that it's lesser than the other two earlier on, right? So your dxy, dyz, and dxz will exist at a lower energy level. Okay, so again, still have some repulsion because they are close by, just that it's not head on, right? So weaker repulsion. All right, so this explains the splitting of the degenerate d orbitals to two different energy levels. Okay, once more, okay, this was the diagram that we showed earlier on. Okay, this is the ion in the presence of ligand, and then when the ligands come close to the metal ion, then your d orbitals will start to split out into two different groups like this. So we will need to know which are the orbitals in the group of 2 and which are the orbitals in the group of 3 for an octahedral complex. Okay, you will need to know this. Alright, now I'm going to show or share something that is not in the syllabus, but it will be good to be aware about this. Okay, now for a tetrahedral complex, right, the 3d orbitals, right, the 5 of them actually will also be split, but very differently. Okay, and the size of the energy gap can vary as well. Okay, so how is it being split? Right, it's split in a 3-2 formation, meaning 3 above and 2 below, right? And the way the way tetrahedral is seen is not the same as the way octahedral is seen. Okay, the coordinate system is a little bit wonky here. The vertical is not the z-axis. Yeah, so you may want to check out how the Cartesian axis is being seen in a tetrahedral complex. Okay, again, there's no need to learn this in detail. Okay, just want to share that it's just a reverse kind of in terms of just the number of d orbitals above and below, right? And this is how it looks like. Okay, for the way the d orbitals are are oriented in the tetrahedral manner. Okay, so in short, okay, these are the ones that will have faced the greatest repulsion, which is actually dxy, dyz, and dxz. Okay, I'm not going to go into too much details here. Okay, just need to know the identity of the orbitals that are above now. Okay, and the two dx square minus y square and dz square, they are below because of weaker repulsion between the point charges and these orbitals. Right, just remember the identity will do. Now we will go into learning about the factors that affect the colors of the complexes. Okay, and the very first one will be that the color of the complex depends on the energy gap, and hence, okay, what kind of factors can affect the energy gap between the two sets of d orbitals. Okay, and you can see that the ion itself, okay, let's say everything is all water ligand, okay, that's the constant now. Okay, the different metal ions itself can actually contribute to the variety of colors alone. Okay, so you can see one of the factors there. All right, so that leads us to part A. Okay, the nature of the central metal atom or ion. Right. So, the metal ion itself, okay, can allow us to predict the type of colors that we see. So, like what we learned from QA, iron 2 plus aqueous will be pale green or green. Okay, copper 2 plus will be blue, and zinc 2 plus will be colorless. Right. And you know why zinc 2 plus is colorless, right? Okay, because DD transition is not possible here. Yep. Okay. And the next one will be oxidation state. So I want to bring your attention to the +2 oxidation state for iron and the +3 oxidation state for iron as well. Okay. And you can see that just by having different oxidation states, the colors can change already. Right? If it's green, then it should be absorbing red. Okay, and if it's yellow, then it will be absorbing violet. Yeah, absorbing violet. Okay, so this tells you the energy gap. So between green and yellow, okay, so this one is absorbing red, and this one is absorbing violet. Okay, which one has a higher energy gap? Okay, so your answer should be yellow. This one has a higher energy gap, right? So that's why it's absorbing red. Sorry, absorbing violet. Okay, the next factor, nature of the ligand bonded. Okay, so the value of the delta E is actually dependent on the type of ligand as well, dependent on, yeah, okay, missing word. Okay, so different ligands can split the d orbitals by different extents. So for example, okay, the classic one will be copper 2 plus aqueous, which is blue, and then when you add excess ammonia, it will turn into a deep blue coloration. Yeah, because of the presence of ammonia here. Okay, another example will be hydroxide and water, right? So you can see that when you are when your chromium is 3 plus is in excess sodium hydroxide, okay, your green PBT will turn into a dark green solution. Okay, dark green solution, and when it's in aqueous form is like in bluish color. So that showcase how different ligands can cause different coloration in your solution here. Okay, now we'll round up this lecture video with a closure like this. Okay, we're going to do a recap. Okay, one more time. Why are transition metal complexes colored? Okay, so let's recap. Okay, this is the main answer to go for. So you start off by saying that in the presence of ligands, okay, the 3D orbitals are split into two sets of orbitals with different energies. Right, you don't need to draw this diagram. Okay, I'm just showing you how it works right now. Okay, so it will split into two sets of different energies. Okay, in the octahedral ligand field. Right, so the blue words will be how you start off the answer, by the way. Okay, now tell us that the difference in energies between the two sets of non-degenerate 3D orbitals is small. Non-degenerate means they are of different energy levels, by the way. Okay, and this energy gap is small. Okay, the difference in energies between these two sets is small, like this. Next, okay, we will have radiation from the visible region of the electromagnetic spectrum, so shine white light. Okay, then a particular radiation will be absorbed so as to allow the electron, okay, to be promoted from a lower energy d orbital to another unfilled or partially filled d orbitals of higher energy. Okay, so this energy gap corresponds to that radiation to be absorbed, and this electrons absorbs that energy and gets promoted like this. Yeah, so just now green light was absorbed, and then the electron got promoted here. Okay, and as such, the color observed corresponds to the complement of the colors absorbed. This is the final phrase for that explanation of this concept. So which means when it will reflect, green is not reflected. Yeah, green is not reflected here because it has been absorbed by these electrons. So hence I will see red, which is the complementary, the opposite here. Okay, and that's how it works. Okay, so this is the last slide for this lecture video. So that's it. And the next lecture video will be the last one for this chapter. Okay, I'll see you then. Thank you.